Hello everyone, I'm Chunyu from Shanghai Jiao University. Today I'm very excited to share our work, MuxTune, which provides a systematic view of multitask fine-tuning in data centers. This work is collaborated with the National University of Singapore. Let's start with a code example of public fine-tuning APIs as offered by LLM service providers such as OpenAI and Google Gemini. As you can see on the slide, with a few lines, users can upload their training data and create a fine-tuning task with customized model, method, and hyperparameters. Here we choose Llama as the backbone and LoRa as the fine-tuning method, which is the most widely used type. Behind these APIs, the cluster scheduler generally launches a dedicated instance for each PEFT task, which includes a set of GPUs and the backbone object with loaded parameters. In PEFT scenario, the backbone parameters remain frozen while we only train adapters with much smaller size. Here we summarize all PEFT algorithms as three categories, including additive, selective, and reparameterized, which all share the standard workflow as mentioned. For example, LoRa, which stands for low-rank adaptation, maintains adapters in parallel to track the weight updates of the backbone operator during fine-tuning. However, we found that PEFT workloads encounter severe performance issues from two factors. First, PEFT has a 1.47x gap in model flops utilization, or MFU, compared to 4 per training. This originates from the small-scale operators introduced by PEFT algorithms, such as LoRa's down projection with rank of 8, which has lower operator utilization but non-negligible latency. Besides, some PEFT corpora generally feature shorter sequence lengths and smaller batch size, such as short text generation. In consequence, the average hardware utilization is degraded. And the problem gets even worse in multi-GPU setups due to the increased stage latencies and device stalls. For pipeline parallelism, PEFT cannot use the technique of zero-bubble pipeline because it has no weight gradient computation for the frozen backbone. Therefore, we cannot split the backward pass into input and weight gradients for fine-grained scheduling. Directly using it in PEFT would undermine throughput by 1.16x compared to the standard 1F1B pipeline. For tensor parallelism, however, since PEFT has smaller input sizes, overlapping communication by splitting computation into tiles would further decrease operator utilization. While the communication stall is reduced, the end-to-end latency may still increase by 1.17x. So to solve these issues, however, we found that existing solutions have critical limitations. The first type is to spatially multiplex the hardware in a coarse-grained manner by directly using NVIDIA MPS or multiple CUDA streams to co-locate tasks. It suffers from memory bottleneck because the backbone occupies most of the memory footprint. As a result, it cannot scale to larger models or more concurrent tasks. The second solution is to reuse the frozen backbone across tasks, which is a very natural idea inspired by multi-LoRa service systems. Task data is batched together for model forward and backward passes. While efficient for serving, this approach may underperform for PEFT scenario, which is fundamentally different from serving. As an example, batching altogether would induce diminishing returns in improving utilization, as we will illustrate later, which enlarges pipeline bubbles with more device idling. Moreover, batching tasks with different data sources would incur a large portion of padding that wastes compute and memory resources. The third intuition is to remain sharing a single backbone across tasks while scheduling their computation to overlap the device stalls. This approach doesn't need inter-task padding to align task data. However, it overlooks improving operator-level utilization as mentioned earlier, so merely using it is not a perfect solution. Based on these observations, we wish to take the advantage of both approaches. So we propose to multiplex the backbone in a spatial-temporal manner. This idea forms a complex optimization space with multiple decoupled dimensions, such as determining the optimal spatial-temporal combination while scheduling multitask pipeline. So we propose hierarchically decomposing the space into 3 levels and solving the unique challenges at each level. At the task level, we find that temporal multiplexing benefits reducing device stalls, while spatial multiplexing improves utilization. To solve the inherent trade-off for these 2 options, we should design cost model and efficient algorithm to search the optimal combination. At the operator level, it is important to schedule the execution in both intrastage and interstage parallelism. For intrastage, we should employ operator-level control to mitigate interference and overlap communication of a task with computation of others. For pipeline parallelism, we should schedule multitask micro-batches to minimize pipeline bubbles with low scheduling overhead. At the data level, we should mitigate the ineffective tokens when batching tasks with different data sources. The common strategies such as data batching or packing into a long sequence either introduce ineffective tokens or waste attention computation. So we wish to design an effective approach to achieve 0 inter-task padding while ensuring high computational efficiency. Based on these insights, we built MuxTune, an efficient multitask PEFT system by multiplexing the shared backbone across independent tasks in a spatial-temporal manner. The system is organized into 4 phases. The first is to generate a multitask model to handle on-the-fly task arrivals based on PEFT workflow modularization. After that, we group tasks into hybrid tasks. Those within the same hybrid task are batched together, while hybrid tasks are temporally scheduled for interleaving. Then we orchestrate the operators of hybrid tasks in 2 tiers, using structured pipeline template to mitigate pipeline bubbles and subgraph-level scheduling to overlap communication in intrastage parallelism. For a single hybrid task, we slice data into chunks and perform chunk-level alignment to remove ineffective padding while ensuring efficiency. We first introduce how we safely share the frozen backbone. We found that existing PEFT algorithms can be abstracted into 4 submodules. Base OP as the operator of the backbone, adapters as PEFT operators, dispatch to prepare multitask inputs, and aggregate to merge output tensors. Existing implementation is not specially designed for multitask, which hard-code the adapter into backbone layer. This requires reinitialize the entire model to add or remove a single task with high overhead. Therefore, we decouple the adapters from LLM codes, dynamically register the task, and attach adapters using PyTorch hook mechanism. Most importantly, we achieve task isolation for both runtime errors and forward-backward computation to ensure no impact on fine-tuning convergence for every single task. The next thing is to navigate the spatial-temporal fusing trade-off. The temporal multiplexing option interleaves all task micro-batches to overlap device stalls, while the spatial multiplexing batches them as one. As you can see on the slide, temporal multiplexing performs better when operator utilization is high, while the spatial multiplexing becomes better on the opposite. To unify these 2 options, we propose a hybrid task abstraction. Within a hybrid task, we use batching, while all hybrid tasks are interleaved scheduling. When scaling to more tasks, the decision becomes more complex. So to find the optimal fusing strategy, we build a closed model to estimate the end-to-end latency of each hybrid task and use a dynamic programming algorithm to minimize the overall pipeline latency. We then orchestrate the operators of these tasks by further grouping them into buckets. Those tasks within the same bucket are scheduled in intra-stage, while buckets are interleaved for pipeline. For intra-stage orchestration, we construct subgraphs for each hybrid task. By clustering computation operators, appending communication operators, and isolating adapters. Each subgraph is assigned a priority based on its topological depth to ensure interleaved execution between different tasks. To schedule subgraphs, we use a priority queue to track all 0-in-degree subgraphs, popping the one with the longest latency and including new 0-in-degree ones in the next step. Computation and communication are performed in different CUDA streams for natural overlap. To schedule micro-batch in pipeline, we found that casual ordering would cause pipeline bubbles. In fact, there are two types of computation homogeneity in PEFT scenario, including consistent micro-batch shapes across iterations and equal forward-backward latency for the same stage. So this inspires us to use a static pipeline template rather than costly per iteration searching and interleave forward and backward to minimize bubbles. Therefore, we propose to run the multitask pipeline in a structured manner. We sort buckets by latency, keeping micro-batches of the same bucket consecutive and early launching as many as possible. We have proven the optimality of this pipeline template, which is achieved by mitigating internal bubbles of the last stage. The last thing is to align data for a hybrid task. Common strategies such as zero padding to a unified length and packing all into a longer sequence either introduce ineffective tokens or waste attention computation. So our solution is trunk-based alignment. As shown in the figure, we first pack sequences of each task into longer ones with a unified length. Then we uniformly partition those packs into equal-sized chunks. The key idea here is that we can adjust intra-trunk task ratio to balance their sequence length difference, and without any attention waste because each chunk would only have one or a partial sequence. To determine the trunk size, we observe a trade-off between compute efficiency and padding reduction. Smaller trunk size reduces padding but may undermine utilization, while oversized chunks would insert more intra-trunk padding. In our practice, we set the trunk size to 16.4. We have evaluated our system across different input sizes, model types, and hardware. Our system got 1.05 to 2.3x throughput improvements compared to other baselines. The improvement becomes larger when testing on better device, while our system reduces memory footprint by up to 5.29x. We also conducted several ablation studies to evaluate our system performance, including speed-up breakdown, efficiency of orchestration, and the effectiveness of chunk-based alignment. So I think that's all my sharing, and thank you for listening.